Hello friends, I am Pablo Giuliani. I'm a theoretical nuclear physicist and an educator, and I work at the Facility for Rare Isotope Beams. Within nuclear physics, we study the protons and neutrons dancing at the center of the atom. Each different combination makes a unique nucleus, but together they form the nuclear chart that extends far and wide with many interesting places to explore. Studying the nucleus, however, is really difficult, and that is because we have an incomplete understanding on how the protons and neutrons interact with each other. It feels kind of like watching a game of chess where no one has told us the rules, and by observing, we're trying to guess some of them. The problem is that observing, in the nuclear sense, is non-trivial. Protons and neutrons are very tiny and energetic particles. Neutrons don't usually interact a lot, and the most interesting radioactive nuclei decay very quickly. On top of all of that, we are only able to observe the nucleus one instant at a time, when an experiment is run. Some of the pieces fly everywhere, and our detectors can catch a few. The challenge is then to put the nucleus back together and learn something about the rules that govern its dynamics. For that, we rely on theoretical models to simulate how the pieces were moving, and then contrast with our observations in what is called the theory-experiment cycle. The big issue in this cycle is that as we make our models more complex, their computationally expense goes up as well very quickly. This further intensifies if we want to perform any sort of uncertainty quantification that requires even more model evaluations. Turns out that at the end of the day, putting the nucleus back together in a realistic way is very hard, and what we need for that is speed.
And we can get speed with the help of a little bit of math. My name is Edgard Bonilla. I work at Stanford University as a postdoc in applied physics. By day, I am at the lab doing mechanical modeling for the LIGO collaboration. And by night, I help my friends in theoretical nuclear physics. Now, how do we make these calculations go faster? To speed up our calculations, the key concept is something called dimensionality reduction, and it works like this. In nuclear physics, our models are oftentimes expressed as parametrized differential equations, stuff like Schrödinger's equation, for example, and their solutions contain all of the information about the nucleus that we care about, stuff like the protons and the neutrons' wave functions. Now, these solutions are also often expressed as very high dimensionality vectors, things with thousands or even tens of thousands of coordinates at a time. However, as we change the parameters of our model, these vectors trace a very low dimensionality trajectory that we call the solution manifold for the model. The low dimensionality of the solution manifold is a key fact that we can exploit to drastically speed up calculations. For example, stuff like the reduced basis methods aim to solve the problem in a low-dimensional subspace that approximates the solution manifold. For problems that are more complicated than that, we can rely on techniques from machine learning, such as neural networks, normalizing flows, and genetic algorithms to find a set of reduced coordinates and reduced equations that better represent our system for computation. Now, let's see how my team is able to put these math ideas into practice.
And now, it's time to take all that advanced math and turn it into some very efficient computer code. I'm Kyle Godbey, and I'm a research assistant professor at the Facility for Rare Isotope Beams. I study the basic properties of nuclear structure and dynamics at the intersection of advanced computing. With these dimensionality reduction approaches that Edgar was presenting, we can now very quickly evaluate previously expensive models and simulations. It's not unreasonable to see 10,000 times speed-ups depending on your problem. While that's obviously impressive just based on its technical merit alone, where it gets really exciting is in all the science that it can enable. There's many groups working on this, but in ours we've applied this to the study of nuclear structure, the dynamics of massive neutron stars, and even to the recoil separator that's actually going to be used in the experiment itself. By pairing all this with an advanced statistical framework, you can now open the floodgates of information and draw inferences on nuclear structure and reactions and propagate that knowledge to the limits of nuclear existence. Along the way, we've also developed a number of educational materials designed to help other people apply the same techniques to the things that they're interested in. And that includes you. If you're interested, you can join us at ascsn.net or check the links at the end of the video.